Hey y'all. So for those of you who missed our lesson on Friday on the vocab of circles and radians versus degrees, this is going to get you caught up. So make sure that you grab your notes packet and get everything down. So the first thing we're going to start off with is the vocab of circles. So the first thing is the definition of a circle, which the mathematical definition of it is all the points equidistant, which means the same distance, from a center point. And of course, that center point in this case is M, which is right here in the middle. So we call this circle M. So the way we denote the circle is with a little circle with a dot in the middle. So all the points on that circle are the same distance from M. So it's all the points equidistant from that center point. For a chord is just a line that goes through a circle but doesn't necessarily go through the center. So in this case, that's going to be OP right here. Okay, so it touches both edges of the circle on either end but doesn't go through the center. So a line in a circle doesn't go through the center. So it could go through the center, like the radius is a very special type of chord, but in general, if we're just calling it a chord, then it's going to be, it's just going to not go through the center. So that would be OP. In this case, hopefully you know what a radius is. You've seen that before. But a radius is a line stretching from the center to the edge. So it's half the diameter, and in this case it's MN. The diameter is just twice the radius, so it stretches all the way across the circle. Probably seen a diameter before too, so in this case it's QU. So the diameter is a line stretching from one edge to another through the center. And I'm sorry, you're gonna have to squish your words in here on your notes, but that's all right. A secant line is similar to a chord, except it stretches outside the circle. So in this case, we're looking at RS. So it doesn't go through the center. If you just were looking at R and S, it would be very much like a chord, but it keeps going outside the circle. So RS is a line extending outside the circle and not through the center. So that's RS. The tangent line is a line that touches the circle on the edge only in one place. So in this case, and I should have given you a letter right here. We'll just call it G so that way it can be OG. But anyway, so that would be this line right here. So tangent line, OG, only touches your circle right here in one place. Okay, so it's a line outside the circle, touching the edge in one place. So like I said, that's going to be OG. All right, arcs. So arcs are pieces of the edge of your circle, and there's a lot of arcs on this circle, but so you could pick any number of arcs. QN is an arc, US is an arc, RU is an arc. You could pretty much pick anything. In this case, we'll just stick with QN. It's probably the easiest to see. So an arc is just a piece of the edge of a circle. Pretty simple definition. We also have some other types of arcs. So each arc can be classified as a different thing: a minor arc, a major arc, or a semicircle. So a minor arc is just an arc that is smaller, can't spell today, smaller than 180 degrees, so smaller than a semicircle. Okay, so in this case, you've got a bunch of minor arcs. You could do US, you could do SN, you could do RU, any of those would work. So I'm just gonna write down US. And when you write an arc, you denote it with a little arc over top of it. So it looks a little bit like a rainbow. A major arc is going to be an arc larger than 180 degrees. And in this case, they're a little bit hard to name because if you said arc UO, well, I don't know if you're going this way or if you're going this way. So you need to give me another letter in the middle to tell me which direction to go. So if you called it arc UNO or UQO or UPO, then I know to go to the right. If you called it arc URO, then I would know to go to the left. But URO would not be a major arc because it's not bigger than 180 degrees. So we're just going to use arc UQO. And that tells us to go to the right. Your last type of arc is a semicircle, which is exactly 180 degrees. So arc that is 180 degrees exactly. So it's going to be half of the circle. So you can just call it QU if you want to. It doesn't really matter which way you're going, but if you wanted to specify, you could call this side of the arc QNU. So that would be a semicircle, arc QNU. All right. Next page. So, can you draw a radius to each point of tangency? If you think you can do this without me explaining it to you and you want to try it, go ahead and pause the video. That's what we did in class. But if you want to just keep going, then you can watch me draw it. So, to draw a line from a radius to a point of tangency, you're just going to draw the radius to the point where your tangent line touches it. It's going to look different on each circle depending on where your tangent line is. But the thing that's special about where the radius touches the tangent line is that it always creates a 90-degree angle every single time. So even if it's a full diameter, you know, a diameter is just twice a radius. So it's going to touch that point of tangency at a 90-degree angle. So what do you notice about the radius in each picture? The radius intersects the tangent line at a 90-degree angle every time. Okay? All right, so if we assume in these problems right here that the lines that appear to be tangent actually are tangent, then we can solve for some missing angles. So in this case, they're telling me that the measure of angle P is 12 degrees, and they want me to find X. Well, this is a radius right here, and this is a tangent line because they said assume that the lines that appear to be tangent are tangent. So that means that this makes a 90-degree angle. So if I know that all the angles of a triangle add up to 180, I can do 180 minus 12 minus 90, and that will give me 78 degrees for X. Okay? All right, this one right here is a little trickier because they give you everything you need, but you kind of have to manipulate the picture a little bit. So if you think about this radius right here, being able to sort of like rotate around the circle, kind of like this, then you can move it and actually have it finish off this right triangle right here. So since all radii are the same length, that's also going to be X. And since this full thing, this full chord across here is 12, this side's going to be 6. So now we have a right triangle and we can find the missing hypotenuse length using the Pythagorean theorem. So what we're going to do is 6 squared plus 3 squared equals X squared. So it means 36 plus 9 equals X squared. So 45 equals X squared. So if you take the square root of 45, you get X equals about 6.7 when you round. So that's the length of your radius there, or your hypotenuse of your triangle, however you want to think about it. Okay? All right. So we've got 3 different types of angles that can be in a circle. The first one we call a central angle. And the reason it's named that is probably pretty obvious. It's in the center of the circle, right? And so that's picture one. Picture one is a central angle. Oops, I should be writing that here. Central angle. And its vertex is at 0, so you could call it angle, O. You could call it angle O, or you could call it angle AOB if you want to. Either one of those will work. And the special thing about that angle, the measure of angle O equals the measure of arc AB. So its intercepted arc is right here because its little arms are reaching out and intercepting this part of the arc right here. And the measure of that angle is always the same as the measure of the arc that it intercepts. So if we say that this angle right here is 40 degrees, that means the arc that it touches is also 40 degrees. Okay, so that's what's special about a central angle. The next angle is an inscribed angle because it actually has its vertex sitting on the circle. So the vertex, we could call this angle P. We could also call it angle APB. We could call it BPA if we wanted to. It doesn't matter. But again, this is called an inscribed angle. If you want to write it up here, you can too. And the thing that's special about an inscribed angle is that the actual angle is half the measure of its intercepted arc, okay? So the measure of angle P equals 1/2 the measure of arc AB. So let's say this time that this angle is 40 degrees. Well, that means that this arc is 80 degrees because the arc is twice the angle. Okay, and then our last angle is called a circumscribed angle. Okay, and the circumscribed angle just means that the angle is outside the circle. So this one has a vertex at A, so we could call it angle A, we could call it angle BAD if you want to, angle BAD, or angle DAB if you like to dab. So the name of the angle again is circumscribed. And this one has a pretty special formula. So the way that you find this one, the measure of angle A equals a large arc minus a small arc divided by 2. And I could get more technical with that definition, but I think that's the easiest way to interpret it. So basically you're doing CE minus BD divided by 2. Okay, so the measure of angle A equals CE minus BD divided by 2. So let's say just for fun, I guess, that CE is 50 degrees and BD is 10 degrees. So the measure of angle A equals 50 minus 10 divided by 2, which would be 20 degrees. Okay, so that would be the measure of angle A. All right, moving on. So this page is full of problems. For example 1, we're trying to find the measure of angle BAC, which is right here. Okay, so the first thing you have to notice is that you have a central angle here, which is 57 degrees, and its little arms reach out to the intercepted arc right here. And so since this is a central angle, you know that its arc is the same measure, so it's also 57 degrees. Okay. All right, so then what you can do is say, all right, well, this inscribed angle intercepts the same arc. Its arms reach out and touch that 57 degrees too. So to get that inscribed angle, I just have to divide by 2. So 57 divided by 2 should give you 28.5 degrees. So that's what that arc would be. Okay. All right, the next problems are similar. If you want to try them on your own before you look at the answers, go ahead and pause and see if you can get them without me, and then come back and see if you get the right answer. If you want to keep going, I'm going to go ahead and do them. So this is 46 degrees right here. They want to find angle X. You don't even really have to deal with the central angle here. You can just say this, this inscribed angle has its intercepted arc at 46. So I just need to do 46 divided by 2, which gives me 23 degrees. Okay. For B, there are several ways to do it. You're trying to find the measure of arc ZWX. That means you're trying to go from Z to W to X. And it's an arc, so you got to go around the circle. You can't cut through any angles. Okay. Probably the easiest thing to do is to realize that this is a semicircle from here to here, right? From here to here is 180 degrees. And then this is a central angle at 46, so its arc is 46 degrees right here. So you can say the whole thing is 180 plus 46, which is 226 degrees. Okay. If that didn't immediately come to you and you did it another way, that's fine. You could also say that this was 46 degrees because these two 46s are vertical angles. And you could say that you knew that these two are a linear pair. So 180 minus 46 gives you 134. And so you could add those three up as well, and that would be fine. Okay? It's up to you. There's more than one way to do this one. On C, you have to remember that your tangent line and your radius make a 90-degree angle. And they tell you that arc BY is 40 degrees. So this is an inscribed angle for 40 degrees, which means that this is 20 degrees because you have to divide by 2. And then if this whole thing right here is 90 degrees, and they want you to find YAC, then you just have to do 90 minus 20, which is 70 degrees. Okay? All right. So that's how to do those three problems. The last part of the lesson is converting radians to degrees. So you probably have not heard about what a radian is yet, but it's another way that we can measure, not really distance, but sort of how big arcs are without using, and how big angles are without using degrees. Okay. And the special thing about a radian is that it's the distance, it's still a radius, but what they're doing is they're taking the radius and they are kind of stretching it along the edge of the circle. So if you took a piece of string and you stretched it along the radius right here, like from here to here, and then you just said, okay, let me take that string and put it on my circle right here, it'll fit 1, 2, 3.14 times around half the circle. So that radius, that length of that radius fits pi times around half the circle. Okay, so a radian is the radius of the circle stretched along the edge. So 1 radian fits a semicircle pi times. Okay? All right. So what we just said, again, is that there are how many radians in half of a circle? Well, there's pi radians in half of a circle, okay, because that radian fits 3.14 times around half the circle. So how many degrees are there in half of a circle? Well, you know that a semicircle is 180 degrees. So that means there are pi radians in 180 degrees. Okay? All right, if that's true, how many radians are there in a full circle? So if there's pi radians in 180 degrees, 1 pi radian in 180 degrees, then in a full circle, right, there's going to be 2 pi radians. Okay? You're going to have to double it to get all the way around the circle. So we're going to do, to convert from degrees to radians and vice versa, if you are trying to figure out what 80 degrees is in radians, then we're going to multiply it by pi over 180. So if we're converting to radians, we put radians on top, which means we're going to put pi on top. So we're going to take 80 over 1, and we're going to multiply it by pi radians over 180 degrees. Okay? So that gives me 80 pi over 180. And you can either simplify that in your calculator if you'd like to, or you can kind of do it in your head. I don't have a calculator nearby, so I'm going to do this in my head. So if you divide this by 2 first, you're going to get 40 pi over 90. And then you can keep dividing by 2, so that's going to be 20 pi over 45. And then I believe you can keep dividing. If you keep dividing by 5, then you get 4 pi over 9. So it's 4 pi over 9 radians. Okay. All right, if you want to convert negative pi over 3 to degrees, you're converting to degrees. So you're going to put degrees on top. Okay, so we're going to take negative pi over 3, and we're going to multiply it. Instead of multiplying by pi over 180, we're going to multiply by 180 over pi. So that gives me negative 180 pi over 3 pi. Okay, your pi's cancel out, so you get negative 60 degrees. Okay, all right, the last two. If you want to try them on your own, you certainly can do that. I need to grab a calculator real quick because I know these are going to require it. Okay. So if we're going 2 radians, then we need to take 285 over 1, and we need to multiply it by pi over 180. So that gives me 285 pi over 180. So in your calculator, you can simplify this. Oh, of course I picked the only dead calculator in the room. Hold on. All right, well, I'm going to do the best of myself. If I remember correctly, it turns into 19 pi over 12. And if it doesn't, that's my fault. But I'm pretty sure it does. So 19 pi over 12 radians is what you get for that. For 16 pi over 9, if you're converting it to degrees, you need to multiply by 180 over pi. And if I remember correctly, you end up getting 320 degrees after your pi's cancel out. Okay. All right. If you are confused about any of that, I need you to be honest with me and let me know in class so that we can go over it. We'll do some warm-ups to help you, but otherwise I am going to trust that you will be responsible for this information and that you are going to just nail it on the test. Okay? All right. See you guys later. Bye.